Hello friends, in the last lecture we have seen the difference between scalar and vector, simple vector operations. Now electromagnetic field theory, we have the vectors of electric and magnetic field. So to give exact location position to the vector in three-dimensional space, we require certain system what is called as coordinate system. In our syllabus, we are going to go through the three coordinate system types: rectangular, which is also called as Cartesian, the second one will be cylindrical, and the third one spherical coordinate system. The mottos of all the coordinate systems are same, but the rules are different. So let us begin with the first coordinate system, rectangular coordinate system, which is also called as Cartesian coordinate system. Coordinate systems are of three types: Cartesian, also called rectangular coordinate system; second one, cylindrical coordinate system; third one, spherical coordinate system. The basic motto of coordinate systems is same: to give a particular position or location of a point or vector into the three-dimensional space. But the ways with these three different coordinate systems are different. Work is same, the rules are different. In Cartesian, also called rectangular coordinate system, suppose a point P we have to locate. The coordinates are represented by capital P in bracket x, y, z. X, y, z gives all the measures of three distances covered by the point P in the three-dimensional space along x-axis, y-axis and z-axis. Whereas the same point P is represented in cylindrical coordinate system as rho, phi, z. Here rho and z are the distances, whereas phi is the angle. The same point P, if we want to locate in spherical coordinate system, it is represented P in bracket r, theta, phi. If we switch from rectangular coordinate system to cylindrical coordinate system, one coordinate we have common, that is small z. When we switch from cylindrical coordinate system to spherical coordinate system, one parameter, one coordinate we have same, that is phi. Okay. Now in rectangular coordinate system, all the three coordinates are measures of length or distances in meters. In cylindrical coordinate system, two coordinates rho and z are the lengths and phi is the angle. In spherical coordinate system, there it is the role of two angles theta and phi, and r is the measure of length. As the names of these coordinate systems describe the rectangular shape, the cylindrical shape and spherical shape, here x, y and z describe the length, breadth and height of a rectangular or parallelepiped. In cylindrical coordinate system, rho defines radius of the cylindrical shape, whereas r in spherical coordinate system describes the radius of spherical shape. So let us start with first coordinate system called as Cartesian or rectangular coordinate system. Now rectangular or also called as Cartesian coordinate system. First of all, we will try to represent a point in the three-dimensional space. So for locating or positioning a point into the 3D space, we require certain references with respect to which the exact location position has to be calculated. So in the rectangular, also called Cartesian coordinate system, there are three axes represented: capital X, capital Y and capital Z, which are mutually perpendicular to each other, which we also call orthogonal to each other. So in the diagram, here it is x-axis, y-axis and z-axis that are perpendicular to each other intersecting in the origin O. X is perpendicular to Y is perpendicular to Z, and Z is also perpendicular to the X. Now in this diagram, I have drawn X-axis, Y-axis and Z-axis in the plane of the paper. Okay, actually this X-axis is one-sided orientation. Okay, so this is positive side. The negative side of X-axis can be drawn in opposite direction. This is minus X. Y-axis in this direction has positive orientation. The negative side can be shown by a dashed line. This is minus Y. The Z-axis, this has positive side. The negative side can be shown like this, minus Z. In this diagram, it will be more clear that the two axes forms a plane. Suppose this is positive side of Y and this is positive side of X, this is positive side of Z. So x-axis ranges from like this, from minus infinity to plus infinity. Y-axis from minus infinity to plus infinity. So x-axis and y-axis forms this plane, and z-axis is perpendicular to that plane. This plane you can consider a horizontal plane. So here, if you talk about the plane of the paper, so y-axis is towards the right side of the plane of the paper in positive, negative towards the left, z-axis towards this one in positive, downwards, negative. X-axis is actually perpendicular to the plane of the paper. So these are the three references mutually orthogonal or mutually perpendicular to each other. In another words, the references can be talked as xy plane, yz plane and xz plane. Let us see in this diagram. If this is x-axis, this is y-axis and this one z-axis. So this plane is xy plane. Now yz plane is represented like this and xz plane is represented like this. Okay, the behind portion can be imagined. Okay, so these three planes intersect again in a single point, what we call as origin. Okay, so either the references are xyz axis represented in capital letters, or xy, yz and xz planes. These three planes are also mutually perpendicular to each other, making 90 degree and intersecting into the point O. Now in this three-dimensional space, if you want to represent any point P, let us take this is the point P, we have to give three coordinates, small x, small y and small z. So what are these small x, y and z? If this is the x-axis, okay, this point P has covered a distance along this capital x-axis. Okay, so this much is x. Okay, what is this y? It is the distance covered by point P along the capital y-axis. So this is y from this point to this point. And what is z? Z, if you drop a perpendicular onto the z-axis, how much height is attained by that particular point on the z-axis from the origin? This is nothing but z. In another way, point P is here. We drop a perpendicular on the xy plane which will intersect here. Let us say this is P dash. From the P dash, we draw a line parallel to y which will cut x here. So this is small x, x coordinate. a line parallel to x-axis cut y here. So this is small y dimension, and if you drop a perpendicular onto the z-axis, the height attained by the point P from the xy plane or from the origin is z. Okay, so if you join the origin to this P dash is in the xy plane, so this line and this line are parallel. Okay, so these are the measures of length x, y and z. This diagram also give you the 3D visualizations of three planes xy, yz and xz intersecting into the origin. So these are supposed to be the references with respect to which we take the measurements of the point P in the three-dimensional space. Now in the rectangular coordinate system, we have seen how to locate a point P having the coordinates x, y and z. So these small x, y and z can have any constant or real number values, maybe positive or negative. Okay, so these are the distances covered by the point P in three-dimensional space from the origin with respect to capital XYZ axis. Now this is the structure I have drawn. I will always draw x-axis oriented like this, y-axis oriented like this and z-axis oriented like this. This I called the orthogonal structure as perpendicular to each other. Along with, they are said to be the right-handed coordinate system. So what is a right-handed coordinate system? If we go from x-axis to y-axis with a screw, okay, so the screw will be moved forward into the z direction, or right hand thumb rule. If we go from x to y, we get z, so it should be positive. If we go from y to z, we get x, so x should also be positive, or z to x, it should be y. Okay, so the representation can be like this: x to y gives z, y to z gives x, and z to x gives us y. So these are perpendicular to each other. This is called as right-handed coordinate system. Now let us talk about any planes we can represent in rectangular coordinate system. The planes small x is equal to constant, small y is equal to constant, small z is equal to constant. X is equal to constant, y is equal to constant, z is equal to constant. Before putting any constant value, if we put x is equal to 0, what is the case? So it becomes a criteria that in the three-dimensional space we have to collect all such points which are satisfying the criteria x is equal to 0. So in the three-dimensional space, x is equal to 0. This is the plane of the paper. From left to right I have y-axis. From bottom to top I have z-axis, and x-axis is actually perpendicular to it. Now I put the criteria x is equal to 0. So I cannot be having the value of x more than 0 or less than 0. So I cannot be beneath this paper, I cannot be above this paper, I have to be on this paper, because on this paper one dimension is y, so it can have minus infinity to plus infinity. The z can have minus infinity to plus infinity, but x is equal to 0. If we put x is equal to 1, I am here at the height of 1 meter or 1 unit, you say. If we put x is equal to 2, I have to increase the height. If we put x is equal to 3, again I have to increase the height. So x is equal to 0 is nothing but yz plane. Now if I take x is equal to 1, okay, so here I have to take such a plane which is 1 meter above or 1 unit above the yz plane. Okay, so this is x is equal to 1 plane. If x is equal to 3, so that plane will be above the yz plane or parallel to yz plane at a distance of 3 units. So it can be drawn like this. Suppose this is a plane infinite in this direction, this direction, this direction and this direction, and intersects x here. So capital X axis, so from the origin to this is the distance x. So x is equal to constant. So this is the plane which is parallel to yz plane, okay, at a distance constant. Now if we take y is equal to constant, so first of all we put y is equal to 0. Y is equal to 0. So y is equal to 0 means we cannot be on the positive side of y, we cannot be on negative side of y, we should be aligned to the position of origin. Okay, x can be anything on positive or negative, z can be anything in upward or downward direction. So y is equal to 0 is nothing but xz plane which is perpendicular to the y-axis. If we put y is equal to 2, so we have to take such a plane which will intersect y-axis in 2 units. So suppose this is 2 units from the origin along the y. So this is the plane which will intersect this y-axis in 2. So this plane is parallel to xy plane. Suppose I take y is equal to minus 2. So on the negative side of the y, I have to put that particular plane which will intersect in minus 2. Y is equal to minus 2. So again it is a plane parallel to xz plane, okay, which will intersect y-axis at minus 2. Similarly, z is equal to constant we can put. So z equal to constant will be a plane parallel to xy plane. Okay, if it has positive value, it will be above the origin. If it has negative values, it will be below the origin. Now let us say any arbitrary point A is given with the specific coordinates to us, and we are supposed to represent it in the three-dimensional space using xyz axis. So let us see in the diagram. A is given the coordinates 2, 3 and 4. It means small x is having value 2, small y is having value 3 and small z is having value 4. So I have to represent this point A in this three-dimensional space using rectangular coordinate system. Now x is equal to 2. So first of all on x-axis I will mark 1, 2. So this is x is equal to 2. Y is equal to 3. So on y-axis I have to mark 1, 2 and 3 units. Z is equal to 4. I have to mark 1, 2, 3 and 4 units. So here we have marked x is equal to 2, y is equal to 3 and z is equal to 4. So from x is equal to 2, we will draw a line parallel to y-axis. From y is equal to 3, we will draw a line parallel to x-axis. This is the intersection point. So this point as lies in the xy plane, I can represent suppose p dash. So it has x coordinate 2 units, y coordinates 3 units and z coordinate as it lies into the xy plane. It means z is equal to 0. So p dash has coordinates 2, 3, 0. Now we want the coordinates a 2, 3, 4. So 2, 3 we have, but we want the z coordinate to be equal to 4. So let us raise the height of this point p dash by 4 units. So here suppose 1 unit, 2 unit, 3 unit, 4 unit. Okay. So these 2 points are at the same height, that is equal to 4. Okay, so this is your point A having coordinates 2, 3 and 4. Now in terms of vector, if you have to represent A bar, so A bar or OA bar is one and the same representation. So here the vector in the diagram can be represented starting at O, ending at A. So this is A bar or OA bar. Okay, so this is starting point of the vector O and ending point of the vector A. So O has the coordinates 0, 0, 0 and A is having the coordinates 2, 3, 4. So for representation of a vector, we always do end point coordinates minus start point coordinates. So here we will have 2 minus 0 ax cap, 3 minus 0 ay cap, 4 minus 0 az cap. Now what are these ax cap, ay cap and az cap? These are called as unit vectors along capital X, capital Y and capital Z directions. Unit vectors, the word unit vectors means the vector is having unity magnitude. Unity magnitude means magnitude equal to 1. So it does represent only the direction of the vector. So AX cap represents direction of x-axis. So one unit here we can represent AX cap. One unit along y-axis we can represent AY cap, and one unit along z-axis we can represent AZ cap. So here I can show AX cap, this is AY cap, this is AZ cap. Generally for unit vectors, small a is specified. The suffix gives you the particular direction of the axis, whether it may be x, y and z. And as we know that x, y and z axes are perpendicular to each other, these unit vectors ax cap, ay cap, az cap, these are also perpendicular to each other. Now the vector representation using rectangular coordinate system in general we can show like this: a bar, ax, ax cap, ay, ay cap, az, az cap. Suppose another vector we have b bar, so it can be represented bx, ax cap, by, ay cap plus bz, az cap. So here ax cap, ay cap, az cap in both the cases are same. These are the unit vectors aligned along x-axis, y-axis and z-axis. Now ax capital A, capital AY, capital AZ or capital B suffix x, by, bz, these are the coefficients of this vector, or this is component of vector b along x-axis, component of vector b along y-axis, component of vector b along z-axis. Similarly for vector a also. For a and b, if in bracket we specify some coordinates, let us say 1, 2, 3, okay, 4, 5, 6. So 1, 2, 3, these are nothing but the values of x, y and z. So in vector representation we have to take capital AX means x coordinate equal to 1 of a, y coordinate 2 of a, ay. So AX will be having 1, ay will be having 2 and az will be having 3. Similarly for the b having coordinates 4, 5, 6, bx will get the value 4, by will get value 5, bz will get the value 6. So a bar will be represented ax cap or 1 ax cap plus twice ay cap plus 3 times az cap. B bar will be represented 4 ax cap plus 5 ay cap plus 6 az cap. Now these are the representation of vectors using rectangular or Cartesian coordinate system. Now let us talk about dot product. Dot product is the multiplication of the two vectors. Earlier we have seen addition and subtraction of the two vectors. Let us talk about the dot product, which is multiplication of two vectors, for example a bar and b bar. Now dot product, also called as scalar product. For vector a and vector b having representations, the dot product is scalar multiplication, the outcome is multiplication. So a bar and b bar are the two vectors and dot is shown in between the two. The formula for dot product is magnitude of a bar into magnitude of b bar into cosine of smaller angle theta between them. So in the space, if this is a bar and this is b bar, so if we take a bar and b bar to have same source point, so this is smaller angle theta between them. The bigger angle theta may also be like this, but according to the definition we should always take the smaller angle theta between a bar and b bar. So magnitude of a bar into magnitude of b bar into cosine of smaller angle theta. So this operation gives us magnitude only, it does not have any kind of direction in between, so it is also said to be a scalar product. Now how to find magnitude of a bar or b bar? So if a bar is having the representation ax cap, ay cap plus az cap, so ax, ay, az capitals represent the components along xyz axis or coordinates, simply you can say. For b bar we have bx ax cap, by ay cap plus bz az cap. So magnitude of a bar is given as under root capital AX square plus capital AY square plus capital AZ square. Magnitude of B bar is given as capital BX square, capital BY square, capital BZ square. The coefficients AX, AY, AZ, coefficients BX, BY, BZ have to be squared and added, and finally the square root has to be taken. This gives us the magnitude. This is actually from the distance formula. In the three-dimensional space, suppose x, y and z axis are there intersecting into the origin and a point P is there. So if P is there in the space having the coordinates, let us say x1, y1, z1, another point in the space, let us say Q having the coordinates x2, y2, z2 are there. If you want to find the distance between the point P and Q, then we have to write mod of PQ bar. So what is PQ bar? PQ bar is a vector starting at P ending at Q. So I can show it like this. This vector started at point P and ended at point Q. The magnitude of that is nothing but the distance between these two. Okay, so this is distance. Okay, so here first of all P bar as a vector we can take, which is nothing but origin to point P. Okay, q bar as a vector we can take, which is from origin to q. So here if you see, this is p bar or op bar, this is oq bar or simply q bar. These are the two vectors. Okay, by the triangle law of addition we can see op bar plus pq bar is equal to oq bar. Okay, so simply pq bar, okay, pq bar is nothing but the oq bar minus op bar, oq bar minus op bar. So oq bar with these coordinates x2, y2, z2, okay, op bar with the coordinates x1, y1, z1, we can simply write the distance formula under root of x2 minus x1 not square, sorry, bracket square, y2 minus y1 square plus z2 minus z1 square. So this is the distance formula. We have seen dot product, which is called as scalar product of the two vectors, represented by a bar dot of b bar, for example. So a bar dot of b bar is nothing but magnitude of a bar into magnitude of b bar into cosine of smaller angle theta between them. So here a bar, b bar and angle theta we have discussed. Now cross product. The cross product is represented a bar cross of b bar. The outcome is a vector. For the dot product, the outcome is having only magnitude, that is scalar, hence it is also called a scalar product, whereas for cross product the outcome is vector. Generally it is calculated by using the determinant, the first row having the unit vectors ax cap, ay cap, az cap, and the second and third row corresponds to these coefficients of vector a bar and b bar. So this is capital Ax, capital Ay, capital Az, capital Bx, capital By, capital Bz. Solving this determinant, okay, will give you the cross product of a bar cross of b bar. Diagrammatically, if a bar and b bar are aligned to have same source point, angle theta between them, a bar cross of b bar, we have to proceed from a bar to b bar with the curled fingers. The thumb will give you the direction of the resultant. So if we get a bar to b bar, the thumb is inside the plane of the paper, which is the direction. So I write inward for a bar cross of b bar. If we have to take b bar cross of a bar, so b bar cross of a bar, so this will be outward or b bar cross of a bar. The subsequent lecture will follow with the numericals based on to the concepts we learned in the rectangular coordinate system. Thank you.